Everyone? Everyone, can you hear my voice?
Yes, sir.
Okay, nice.
Yes.
At least somebody did reply.
And it's me again, not surprising.
I think I can give you full attendance for you. A full attendance.
Yes, sir. Don't come anymore, sir.
Yeah. Okay. So we continue with question number 20, the last of paper number paper model paper 1. Okay, a cylinder filled with movable piston contains 0.70 mole of diatomic gas, ideal gas. The initial state A, at the initial state A, the pressure of gas is with this amount of pressure and volume with this amount of volume. Then the gas is taken from state A to state B and then to state C as described below. A to B is isothermal. Isothermal means that uh, it will be moving in isotherm curve. Expansion to a volume to a certain volume over here, and then adiabatic compression is compressed, okay, to the same pressure in state A. So if we have a PV graph, okay, draw a PV graph to show the changes of state in the gas described above. So let's see, we assume that this is isotherm curve. One temperature, second temperature, okay. So again, using us from A, okay, from A, okay, it goes to B. From A to B, it will be isotherm. So A to B, and over here, it will be isotherm because it follows the same isotherm graph. As the isotherm, it means that it's same temperature. It follows same temperature. So A to B. So I put the arrow. This one is as an arrow. This is A to B. This way. And from B to C, it says that it will be compressed. Okay, we compress. B to C is a adiabatic compression. So isobatic does not follow the same temperature curve. So B to C goes up like this. Okay, this is C. So this is A, this is B, and this is C. Okay, so we can make an area over here. A, C, and B. A and C has the same pressure. This is PV graph, remember? So A and C, same pressure. So here we have V1 and V2. Okay. So V1, V2 is bigger than V1, as you see is mentioned in the question. Okay. Now we have a graph of it. Number one, A1. Okay, number two, use the ideal gas equation to determine the temperature at gas A. Okay, at gas A. Uh, to get the temperature at gas A, you can use the ideal gas equation. That is PV equals to nRT. Okay, so T is 3 over 2 times 3 times 0.2 times 10 power 5 uh, times with 4.8 times 10 power of negative 3 and divided by 0.7 and 8.31. So you have T equals to 264 Kelvin. Okay, you got this answer, number 2. Everyone, do you got the answer? Or you have different answer?
My answer is wrong.
The answer is how much?
Way off.
Way off, okay. So did you use PV equals nRT?
I forgot what I used. I think I was
Okay,
drunk that day.
Okay. So it's proven that it's only you that listening to the class. Okay, let's see. I read to the
Others all
chat.
shy lah, sir.
No, they even reply on the chat. See, I put hello. No one replied. Okay, A B1. B1. Find the pressure of the gas in state B. Okay, so work done by the gas on state B. Base is replying at least.
See, you see, may reply.
1 over 2 over
They will
9.
answer, eh?
2 over 8. Okay, it's 2 over 8. There are 8 people over here. 8 people and 2 are answering. Trying, sir. Okay, maybe also. Okay, find the pressure of the gas in state B. So A to goes to B, you know that the PV is constant. Right, PV will be constant. P1, V1 will be equal to P2, V2. This is constant. So we can use at state A and goes to state B. We can use that P1, V1 equals to P2, V2. Okay. So P2 equals to P1 V1 over V2, right? Is it? Yeah. So it will be equals to 4.8 times 10 power of negative 3 divided by 7.2 times 10 power of negative 3 and times with 3.2 times 10 power of 5 Pascal. So you have 2.1 times 10 power of 5 Pascal. Okay. So this you just use the P1 V1 as a constant. P1 V1 equals to P2 V2. Then you can get the how much for pressure at the B. Okay, number 2, work done by the gas from A to B. So A to B, you can use also the area under the graph. Where is the area under the graph? It's actually this side, A to B. Down there will be the area under the graph. You can use that method, okay? Or you can use the equation method. The equation method is, okay, uh, where is it? Where can I put my drawing? Here. So number 2, you can use W equals to nRT and ln V2 over V1. Actually, this is a derivation of the area under the graph. So there you have n 0.70 times with 8.31 ln with 7.2 times 10 power of 3. Is it 3? Negative 3 divided by 4.8 times 10 power negative 3. As a result, the answer will be 623 joule, 623 joule. Okay.
So what formula is this from?
Mm?
What
This
formula
one,
is this
this
from?
derivation, it came from the area. How to get the area under the graph? Because from A to B is a curve, right? A to
Yeah.
B is a curve, and then you have to find how much the area of the curve. Then you have the ln here. Actually, it came from the ln. Any question? Others? I want to turn on my light. Any question? Everyone? Anyone here? B? Maybe? Any question? You have anything to ask? No. No. Okay. So, What is the temperature of the gas in state C? Okay, we continue with question number C. What is the temperature of gas in state C? So C goes up again, and you have a C. Okay, C does not have the same temperature as A to B. So W equals PV only used when the pressure is constant. Pressure constant. The work equals to PV when pressure is constant. Pressure constant. What do you mean by pressure constant? Pressure constant, it means that there will be one line over here. If it's constant, let's say pressure is constant, there will be one line over here. A PV. Ah, correct. Yes, it is. Of course, P times V is a rectangle. Is a rectangular. Correct. Yes. Yeah, you are correct. If a pressure is constant, of course you can see over here. This is PV graph, and then you have a PV. P is constant, means that like it will be like this, right? So the area on the graph is a rectangle. So P times V. That's the area on the graph. Okay. But yeah, you are correct. Okay. But if we have a curve graph, in this case, we have to use the ln V2 over V1. Okay, Jihao? Okay then. Okay, so we continue with C. Now we goes back to C, up to C, and the C does not have the same as temperature A to B. It will be different. Okay. So remember, when you have adiabatic, remember you have the equation that is TV gamma minus 1 equals to constant. Remember that. Okay, if you check your adiabatic equation, there will be TV and TV and PV. Okay, so TV gamma minus 1 actually is constant. It means that T1 V1 gamma minus 1 means the first state is equals to T2 V2 gamma minus 1. It will be equal. So it means that from B to C, from B to C will be equal. Okay, by the gamma. Okay, so what we can do is, what is gamma actually? What's the value of gamma? What's the value of gamma over here? Who can tell me what is the value of gamma? Anyone here? What
Is
is the
it
value of
the
gamma?
diatomic monatomic constant?
Yes, the value is
3/2.
3 over
Monatomic,
2.
right?
This is
Oh,
diatomic.
diatomic. 5/2. 5/2.
5
5/2.
over 2. F plus
No.
2 divided by F. So it is a what? Degree of freedom plus 2 divided by degree of freedom. So you say it's 5 is correct. Now it's actually how much, Tony?
7/5.
It's 5 plus 2 divided by 5. So 7 over 5. The gamma is 7 over 5.
Forgot already, sir.
Yeah. Okay. So 7 over 5. And then remember 7 over 5 with minus 1. Because you can see the formula here. Gamma minus 1. Okay. So I put out next slide. Okay, clear it out everything. So TC, temperature at C, equals to 7 over 2 times 10 power of negative 3 divided by this is the volume 4.8 times 10 power of negative 3 in the bracket 0.40 because gamma minus 1 is the value of gamma, and times that with the temperature at B, that is 264 Kelvin, and you end up with 310 Kelvin. So it means that from A to B, the gas was having a temperature of 264 Kelvin. But when the B comes to C, B was automatically compressed to C. The temperature was higher, that is 310 Kelvin. Actually, it's not the curve. This one will be the curve at this point. 310 Kelvin over here at that point. Okay, I suppose everyone already understood what I'm talking about. Okay, so D1 describe how the gas can be brought back to initial state from A to C. A from C. Okay, so from C goes back to A. So how can we do that? What we can do is, because it has the same pressure, C to A, same pressure. So what we do is D1. What we do is compress the gas at constant pressure until volume is 4.8 times 10 power negative 3. It means that you compress because C has its own V and A has its own V. So we just compress it until the V is equals to 4.8 times 10 power negative 3. You just compress it with a constant pressure. Okay, show the process in the PV graph above. So this will be the graph. So AC to A. Okay. Y is represented by the area enclosed to a circle in PV graph. Find the value of this area. Okay. E is, okay, he says that what is this area actually? This area. Okay, the closed area of A, B, and C, and goes back to A. Actually, the value over here is, we call a area enclosed is a network. Network is not work. It's a network, means that plus minus with all the works or all the things we have done. This is the net of it. Network done on the gas in a complete cycle. Okay, so whole cycle A, B, B, C, and goes back to A. This will be the network of gas. Okay, network of gas done. Okay, CIS actually is analogous like this. You have a box. You move a box this side. Okay, and then you move box to the right, and then you move back a little bit to the left, and then the box are here, right? So how much the network done is actually the difference between A to B, right? So work net done is actually at this point, right? This is the work done net. Okay, right? Although you push it to A and then you push back to B, then network done is actually over here. This is same thing. Network done is all of, and you plus and minus all the work done. Okay. Find the value of this area. Okay. To find the value of this area, again I have to A to B, B to C, C to A. Okay. First B to C, B to C. the Q, uh, the heat quantity, okay, equals to 0, okay, and equals to change of U plus W, thermodynamic law of the thermodynamic, first law of thermodynamic. So W equals to change of U, uh, internal energy of the gas, equals to N, that is 5 over 2 R change of T from B to C. So you have here the value is if you substitute everything, it is 5 over 2 and 0.70 times 8.31 and 310 minus 264, then you have negative 669 joule of energy or work. Okay, B to C, oh sorry, this is A to C, A to C. B to C, okay, you can use PV gamma equals to constant, okay, B to C, because B to C is a adiabatic, okay. Uh, so you have a 3.2 times 10 power 5 V C, that is 1.40 equals to 2.1 times 10 power 5 times with 7.2 times 10 power negative 3, 1.40, same gamma. It doesn't, it was 7 over 5, you divided 7 over 5, you get 1.40. So VC, you have 5 point, this is volume for C, times 10 power negative 3 meter cube. Okay, C to A, C to A, C to A, work done equals to P change of V, and 3.0 times 10 power 5, change of V is 4.8 times 10 power negative 3 minus with 5.3 times 10 power negative 3. It came from here, down here, and we have work equals to negative 160 joule. So area enclosed is your minus 160 plus 669 minus 623 joule. There you have 206 joule. So area under here, okay, no, the area over here is at least 206 joule. Okay, any question? Any question, anyone? No, okay. So we have finished first set of model paper. Okay, we're going to continue with we have 10 minutes. We can continue to the next paper. Okay, so this is the second set of paper. Okay, which following example of random error? Tony, if you are there or anyone alive there, if you still alive, can you give me the answer 1, 2, and 3? First answer, number 1. What is the following example of random error? There are two kinds of error. One
Okay,
is
so let me
random.
find my paper.
Two kinds of error. One is random, one is systematic. Puyi and Maybe says D.
I say
Reaction
D also.
time involved in starting or stopwatch. No, answer is C. When you
Why?
because A, B and A, B and D
And D?
is systematic error. Okay, systematic error. Meanwhile, C is a random error.
I don't understand, sir.
Systematic error. Remember what is systematic error? Systematic error is the error because of the apparatus itself. Okay, or
Mm-hmm.
the measurement of itself. Random error is the error made by yourself.
Yeah, lah.
It's big
Reaction time, sir.
reaction time.
Yeah, ourselves, right? Our reaction time is not certain, right?
No. Okay, reaction time involved in starting a stopwatch. Random error starting a stopwatch. Yeah, maybe it's D. But I the most the most obvious is actually C. Stopwatch to 0. Okay. Uh, Magnitude of error are not constant. Yes, magnitude of error is not constant. One more thing, characteristic of random error, the magnitude of error is not constant. That means that it doesn't have any uh consistency of it. Okay, number two, acceleration can be determined from answer. Number two, acceleration can be determined from
I think it's D. Gradient. Yeah, D.
yes,
Whatever I say
correct.
D.
It's a gradient of velocity time graph. Correct. C B three number three.
I put B.
Yes, answer is B. Okay, you can use two method. There are used two method. One is by using graph. You have a VMS over TMS. Then you have from 50 and goes down to 5. Down 50 goes down to 0, and this is 0 to 5 second. Okay, 5 second. No need repeat PY. Okay, so here will be the from 40 to uh, from 40 to 30. So you can get how much the area on the graph. Okay, 1, or you can use V square equals to U square plus 2AS. V is 30 squared, U is 40 squared, and 2 times negative, how much is negative 10, right? Negative 10, and then you have a time. Okay, number number 4, what will be the answer?
So Mayway and Pui not happy, is it? So
Action time, no need repeat PY is mean? What?
the you not happy with the first answer, so
What important need? What important need repeat 3 times? Action time different. No need PY. PY is mean what? No sir. Are you nothing teacher? Okay. Okay. For for basic of uh, for basics of physics, magnitude random error is because of yourself. Okay, systematic error is because of the instrument. So random error is because of the why we call it as observer. We the one who did it. Okay. Uh, Answer 3 times for each question. No need answer. Yes, systematic error involve human limitation. Systematic. Yes, one more. Okay. But the main point is random error. The error will is not constant. If you have a, let's say you have a ruler and you measure it 5 times with this using the same ruler, you have a we call a systematic error. It's because of the ruler itself is broken. Okay. But when you random error, okay, when you repeat and repeat, and you repeat again, the number will be different. Systematic involve pattern ma no me? Yes, it involve apparatus. Okay, this is what I call systematic. Okay, can I go? Oh, we have 1 more minute. Okay. Am
So could be D also, right?
Yeah, it could be D, but the most obvious is C
Um,
actually. Okay,
damn it.
the most obvious actually. Most obvious is D. Um, Reaction time involved in starting a stopwatch. Yeah, because you are involved. You are the one to making
So
the
in
what?
general, D lah.
Forget to reset the stopwatch. Actually, it's D also can, but C is much more obvious. Forget to reset stopwatch to 0. Inconsistency. I mean, when the area you produce is not consistent, this is what we call as random. Okay, time's up already. See you next time. Okay.
Okay, sir.
Okay.